Okay. Great. Okay. Good afternoon, everyone, and welcome to today's Galford seminar. Before I introduce our speaker for today, I just have a quick announcement. Yeah, I mean, we want you guys to suggest speakers for who you'd like to hear. So there's a form to submit anybody who you'd like to speak, and I'll just pop that in the chat now. Okay, I'll do it in a bit. But anyway, right. So today's speaker is Prof. Annalisa De Cia. Prof. De Cia is an assistant professor at the University of Geneva. She studies gas, metals, which is what we call the chemical elements in the universe that are heavier than helium, and dust in galaxies using background sources to shine through them. Recently, she was awarded a Prima grant by the Swiss National Science Foundation to build the Interstellar 1 research group. And for more information about her work, you can visit her website at annalisadecia.com. I'll also put that link in the chat. And today she'll be talking to us on a chemical universe, gas, metals, and cosmic dust in nearby and distant galaxies. All right, take it away, Prof.
Thank you, Shilpa, and well, thanks all the organizers for inviting me and for being here today. Maybe can one of you or something or more have the video on while I talk, so that I have the feeling that there's somebody on the other side of the screen. Anyone is up for this? Thank you. Thank you. Very nice. Thank you very much. It is nice. It makes it a little bit more human, despite we are so far away. So I will share my screen now. Do you see my screen? And does it move? Yes.
Yeah, all good.
So I can start. A chemical universe. So today we'll talk about gas, metals, and cosmic dust in the nearby and the distant galaxies. I wanted to really start from this basic question. What is a galaxy? What you can see here is a beautiful image of the Andromeda galaxy. But what you can actually see is light that comes from stars. But I'm here to tell you that there is much more to a galaxy than only stars. And one fundamental ingredient that is missing in this picture is gas. So if you take gas into account, then this is a newer picture of what a galaxy is. This is now an artistic impression, is a drawing. And in the middle here, you see my cursor? In the middle here is the stellar disk, now on much smaller scale here. And all around and inside this galaxy, there is gas. There is gas that comes from the outside, from the cosmic web. It accretes onto the galaxy. And when it accretes, then star formation can happen. And the stars, then they will form metals, so all the heavy elements. And then more gas will be blown out, more metals, and some of this gas will be recycled and some will be blown out in these outflows. So gas is absolutely a fundamental ingredient for how a galaxy is formed and how a galaxy will evolve. And this is actually observed even for our Milky Way. This is, we observed gas streams and hot gas that is very important for the galaxy formation. On the left hand here, you see observation of H1, which I imagine that some of you are interested in with radio telescopes. So in here, like you can see the galaxy, the stripe of the galaxy, so the galactic plane. And then you can see the Magellanic Clouds and what is called the Magellanic Streams. So even our galaxy is not an isolated island. There are streams of gas all around the galaxies and their satellite galaxies. And on the right hand, you see then a simulation of gas. And it turns out that to reproduce the observables, like the observations of the gas that we can see, you have to include large amounts of hot gas in the process of galaxy formation. Of course, this gas has a number, very different temperatures and phases and ionization. What I will mostly focus on today is the neutral interstellar medium. So the gas more or less inside, in between the stars, but not only, it's like actually more extended. The one that is neutral is dominated by neutral hydrogen. And it encompasses the cold and warm neutral medium and the diffuse molecular gas. In this picture, it's from a simulation, the neutral, so it's a simulation of galaxy formation and evolution. So you will see, here you see H1 gas, so the different colors show different densities. And the neutral gas, the one that is dominated by neutral hydrogen, is the one in green. This gas is crucial for the formation of stars and molecules. And what is it made of? So it's mostly hydrogen. Then there's a bit of helium. And there's 1% metals, meaning all the elements heavier than helium. And this 1% is so important, although it's so tiny, it's crucial for the formation and evolution of galaxies, for the formation of stars. For example, metals and dust are an important coolant for the very formation of stars. Then metals are fundamental for the formation of dust. You cannot get cosmic dust without the metals. And they are fundamental for the formation of molecules and fundamental for the formation of planets. So really, the metals in the neutral interstellar medium are fundamental for all these astrophysical processes. Cosmic dust is very important. Well, I told you it's necessary for the formation of stars, planets, and molecules. But on top of that, half of the interstellar metals are locked in cosmic dust. So half of the metals are more or less in dust. And even if you don't care about dust, you should know, or we should consider that dust reprocesses about half of the non-primordial light. So it absorbs the light in the UV and some optical frequencies and re-emits it at longer frequencies. I hear some background noise. Maybe somebody can mute. About the origin of dust, there is still an ongoing debate because we still don't know whether it's they are produced by supernovae. That's maybe the ejecta cool down and some seeds of cosmic dust particles can be created, or whether AGB stars, so asymptotic giant branch stars, could be producers of dust. But it turns out that we think that the interstellar medium itself could be important for the production of dust in the dense parts of the interstellar medium, and also maybe in the more diffuse. What is the composition of dust? Well, there are carbon-rich grains on one hand, but then there are silicate grains, and then iron-rich grains. And in fact, this iron-rich grains is something that it's coming up now. It's not yet an established notion, but I will come back to this point later. So I told you that metals are important. Metals in the neutral gas are important, but how do we probe these metals in the neutral gas? Because we have a problem. Gas is not bright. It's very difficult to observe because it doesn't emit brightly, and the metals also, they don't emit brightly. So how do you observe it? And the way to do it is through absorption-line spectroscopy. So here you see a cartoon that explains simply how this technique works. So we use a background source, which is A here, and this can be a quasar or a gamma ray burst or a supernova or a star. And the light from this source shines through a galaxy, for example, or some gas, and then we observe it on the other hand with a telescope, like with a spectrograph, either in space or on the ground. And here you can see textbook spectrum of a GRB afterglow, which otherwise would be just a power law, like featureless, but you can see all this absorption, which is caused by the gas and the metals and the molecules in the gas of the host galaxy. This technique is extremely important because it allows us to observe galaxies that are very tiny, very faint, very distant, and not bright, but still we can observe them with this technique. So this technique is very complementary to flux-limited studies of galaxies, which pick up the brightest ones. With this technique, absorption-line spectroscopy, we can also study the fainter ones. And remember that the fainter galaxies are the most numerous. So I mentioned different targets that we can observe. So if we observe stars, then we need to go in space to observe the absorption lines towards this line of sight, because most of the absorption lines are in the UV, and the atmosphere blocks the UV, so we need to go to space. So for example, observe with the Hubble Space Telescope, and then we will be observing the interstellar matter inside our own galaxy. Or we could observe objects that are much more far away. For example, we could observe quasars. And then there will be quasars in the background, and we will study basically galaxies along the line of sight closer to us. And then we will study systems that are called damped Lyman alpha absorbers, DLAs. These are H1 dominated gas, so dominated by a neutral hydrogen. And they are the largest reservoirs of neutral hydrogen in the universe. And more than that, these are the largest reservoirs of metals at high redshift. So these systems are really associated with galaxies with a very wide range of masses, including the low masses ones. And importantly, the low mass galaxies are the ones that are the more numerous. So mostly these systems have low metallicity, and sometimes, very rarely, we get metal-rich ones. And here you can see some photometry of some of these galaxies, which are observed in absorption, but really to see them in emission is quite difficult, in fact. So some of them, we don't see them as, in a picture or in emission. Another object that we can study is gamma ray bursts. So gamma ray bursts are stellar explosion, very violent and very bright, that last for a very little time, maybe a few hours or a day or so. And the interesting thing is that these explosions, they happen all the way to the very distant universe. So we can use them as cosmic beacons to allow us to study their host galaxies and systems along their line of sight. Here you can see the redshift distribution of gamma ray bursts, and you can see indeed that we can observe gamma ray bursts all the way to redshift 8 and above 9. Importantly, this kind of objects select star-forming and small galaxies. And remember that these galaxies, these small galaxies, are the ones that are virtually invisible to normal techniques. And this is an example. This is GRB 130606A. This tells you that was exploded in 2013. That's how we name it, on the 6th of June. And this exploded at redshift 6. And it took 3 hours of deep HST observations to get only a simple detection in one filter of the galaxy hosting the GRB. On the other hand, the gamma ray burst afterglow was so bright when it came off that we could take a nice X-shooter spectrum and really observe the abundances of different metals, oxygen, sulfur, silicon, iron, aluminum. So these GRBs are so bright, are very powerful, and they give really a strong, like an incredible opportunity to look into these host galaxies. So back to this technique itself, absorption-line spectroscopy. But what can we learn really when we take a spectrum of these sources? We can learn many things, and I listed here a few of the most important ones. And well, number 5, the molecular content, then the local environment of these explosions or phenomena, the kinematics, how things move, the dust to metal ratio, so how much dust with respect to how much metals. And first, I put the observed metal abundances, and I will focus a little bit more on this last one, but let me just give you an example of each of this one. So what can we learn with absorption-line spectroscopy? The molecular content. Now, what you see in this plot is this Y over iron. It's basically a measurement of how much dust you have there. We will go back to these relative abundances of metals later, so you will understand a bit better what it means. But for now, take it that this is the amount of dust that we see from measuring the absorption lines of the metal. And here, you see a quantity that is the amount of metals. So here you can see systems towards quasars, they're the gray, the diamonds, and then towards GRBs, which are the circles. And some of them have detections of H2. And molecules are, of course, important because then it's where you get the star formation also going on. It's really where all the actions are happening, where all the action is happening. So next thing that you can learn from absorption-line spectroscopy is the local environment. I mentioned before gamma ray bursts. So when you have an explosion, there's so much radiation from the GRB that it comes through the interstellar medium and it does something to that interstellar medium. And what it does is ionizing and exciting this gas. And if you are quick enough to observe this, like to take a spectrum just after the GRB and maybe after an hour or something, you will see spectral variability of the lines, which means that you have observed live the gas that is reacting to a GRB. And this is what you see on this plot. These are basically lines. They're in absorption, but now they are in a unit of apparent column density, so they look like in emission. But the different colors, like blue and black, are for different epochs, and they change because of the effect of the GRB. And from studying these lines, you can tell really the physical distance between the GRB and most of the gas that was absorbing. And this is fantastic because these are galaxies that redshift maybe 2 or 3 or 4 or more. And it's such a very detailed information that you can get. And of course, you can study the properties of the gas and the physical properties of the gas and chemical properties. Another thing we can learn from absorption line spectroscopy is the kinematics. So really how the gas moves. Does it move towards us or away from us? And are the different clouds, they have different chemical properties and kinematic properties. So Boucher et al. Observed gas that is inflowing and outflowing, looking at the kinematics of the gas. So really components of the gas that are at a different velocity with respect to the main velocity of the galaxy in this cosmic flow. And on the right side, you can see actually a spectrum from specific absorption lines from GRB afterglow. And you see that there's 2 complexes, like the AB is on one side, and then there's CDE on the other side. And this is observed in most lines, like chromium 2, magnesium 2, iron 2, manganese 2. But then there's a strange line here. This is iron 2 with an asterisk. Asterisk means that it's excited. And excited means that it was produced by the GRB. The GRB went there and excited that ISM. And you see this one only in one of these complexes. You don't see this iron excited line in the CDE. And that is because this component here, it's the closest. So the closest component, like the gas that was closer to physically closer to the GRB, reacted to the GRB radiation. And the gas that was far away, it was not excited. And in this component, like the colder component, the further away we could even see molecules, for example. So it's really powerful. And another thing that we can learn from absorption-line spectroscopy is the dust to metal ratio. So how much this DTM, dust to metal ratio, is the amount of dust with respect to how many metals you have. And until recently, the normal assumption was that this ratio is just constant. And through absorption-line spectroscopy of quasars and GLB afterglows, we discovered that this is not true. Actually, it's very difficult to observe the dust to metal ratio for distant galaxies, first of all. But with absorption-line spectroscopy, you can do it. And we found that it's actually increasing with metallicity. Why is this important? Because you can have an increasing dust to metal ratio only if there is an important growth of the dust grains inside the interstellar medium. And this, of course, has an impact of what we think is the origin of the dust, or how the dust builds up. And one more thing that we can learn from absorption-line spectroscopy are the observed metal abundances. So here is this is how we do it. We observe lines from different metals, and we model these lines. We get column densities. So it's basically a measurement of how many atoms you have along the, on a unit of surface. Is this n's, and then we use this notation. So we refer to abundances with respect to hydrogen. And this is in this funky square bracket, which is basically a ratio between the column density of your metal X with respect to the column density of hydrogen. And all this normalized by the same ratio for the sun, which is this, or dots here. And this is in a logarithmic scale. So 0 here means solar, and 1 is 10 times solar. So these are abundances, and relative abundances are relative abundances of element X with respect to element Y. So it tells you the difference, like the differential abundance of one metal with respect to the other. And we can learn about all these abundances, but then how do we interpret them? Because there's really a challenge to understand these abundances, because different processes play a role in shaping these abundances that we observe. On one hand, you have the overall metallicity of the gas, and on the other hand, you could have nucleosynthesis signatures. So some stars that produce some metals or other metals. Then you could have ionization, which is an important effect for some gas, but for the neutral gas, the one that has a high neutral hydrogen column density, the one that I'm focusing on, ionization doesn't play an important role because the hydrogen itself shields the metals from ionization. And then there's the dust content, because some of the metals, they like to be incorporated in the dust grains, or they're missing from the observable phase, it's X over H. And this is really the hardest of these processes to understand. And well, maybe not the hardest to understand, but definitely is the elephant in the room. If you want to understand the metal abundances, we need to understand dust depletion. So now I will stop for a moment and give you a recap. So neutral gas and metals are key for galaxies, stars, molecules, dust, and planets. However, we have a problem that gas is not bright. Faint galaxies are typically missed, but they are the most common. And then on the other hand, we can use, well, gas-selected galaxies are smaller and faint, and they carry most of the neutral gas and most of the metals of the high distances. Then we can use absorption-line spectroscopy to probe these metals in the neutral gas of galaxies, and then we can get the chemical abundances. But then the problem is understanding this chemical content, and it's challenging because of the presence of dust. So we need to understand dust depletion. So what is dust depletion? Dust depletion is the fact that metals are missing from the gas phase because instead they are incorporated in the dust grains. Here you can see the abundance of different metals with respect to hydrogen. And 0 here is solar metallicity. And here you can see measurements that have been made in the galaxy for different metals. You see, for example, nitrogen here, oxygen, there's zinc, and so on. Like here, down here, you have chromium and iron at lower abundances, and titanium, for example, down here. So these low abundances mean that a lot of these metals are just missing from the observable gas abundance because instead they are incorporated in the dust grains. So if you would measure, for example, an abundance of iron or an abundance of titanium in the galaxy or in other galaxies, this is not the metallicity. No. This is just the metallicity minus whatever is missing because of dust depletion. So if you want to work out really the real content of metals, we have to take dust depletion into account. So in this classical scheme, there is an old approach to study the interstellar medium, metals on one hand, or the dust. So for the galaxy, the Milky Way, or the Magellanic Clouds, one could assume a metallicity, for example, this solar metallicity here, and attribute everything that is missing from there to the dust, and use this assumption to study then the dust. On the other hand, if you want to study distant galaxies, it's not possible or it doesn't make sense to assume a specific metallicity, because we know that distant galaxies probably have a lower metallicity because they're more primordial, and so we cannot take this assumption. So the assumption then reverses, and until recently people assumed that there were either no dust grains, or if there were dust grains, they had exactly the same properties of the Milky Way. And then you use that to study the metallicity of the gas in those galaxies. And recently I developed a new approach to study metals and dust, both at the same time, without making any assumption on what is the metallicity of the gas, nor what is the dust type. I just wanted to study gas in galaxies at any redshift. And importantly, I had to include low metallicity systems, so these quasi-DLAs, for example. And the trick was focus on the relative abundances instead of the abundances, the absolute abundances. Well, how do I do that? Well, here I report just the definition of the relative abundance for your information, or to remind you. And I considered, on one hand, relative abundances that would be dust tracers. This is the x-axis. And here I have zinc over iron, but there could be others, like silicon over titanium or oxygen over silicon. There could be others. The important thing is that the two elements, they have very different ways of depleting with respect to each other. So one likes very much to go in the dust, and the other not so much. And in terms of nucleosynthesis, they overall follow each other. And on the other hand, on the y-axis, one can estimate what is the amount of the element X in dust by using relative abundance with respect to Y, where Y is an element that is non-refractory, so it's not very much depleted. So in this sense, then, this quantity X over Y is dominated by the depletion of X. And when I did that, I found beautiful correlations that were valid for very many different galaxies, all the way from local to distant galaxies. And this was really the key that allows the community now to use observed relative abundances and work out the dust depletion using techniques from these different papers, and then separate the properties of the metals and the properties of dust and study both. So this is an example of what they call the dust depletion sequences for different galaxies, both local. So we have the Milky Way in orange and the Magellanic Clouds in yellow and green, and then the blue for the distant galaxies, the DLAs. So the x-axis is the zinc over iron that tells you how much dust you have, all the way for the systems that have less dust to the Milky Way that has like the highest amount of dust. And these are the depletion sequences, or the depletion of different elements. The very fact that these sequences exist and they are valid for environments that are so different, distant galaxies, Milky Way, Magellanic Clouds, this very fact tells us that there must be some sort of common dust production mechanism. And we think that growth in the interstellar medium could be the mechanism that is at least important to build up a large amount of the dust that we observe. Another thing that we learned from the studies of dust depletion is the dust to metal ratio that increases with metallicities. I mentioned before. So here you see a similar plot than before, so that with the dust to metal ratio that increases with the metallicity, this M over H total is the dust corrected metallicity, the total between dust and metals, gas. So the metals in the gas plus the metals in the dust together. And it increases. And I just wanted to show you this because if you want to reproduce with some modeling an increasing dust to metal ratio, you have to have grain growth in the interstellar medium. These lines here are for reproducing dust to metal ratio, including efficient grain growth in the interstellar medium. Another thing that we learned from studying the abundances, the cosmic abundances, is the cosmic chemical evolution. So how much metals are out there really? Well, we found that there's 3 times more metals than what was previously known. So what you can see here is this the metallicity, the total metallicity in terms of the iron. So the iron abundance, like the total after including the dust corrections, with respect to the redshift or the cosmic time. And these measurements are for quasar DLAs. So the quasar DLAs are these distant galaxies. These measurements are for the quasar DLAs, the yellow ones, and the red points are their averages after waiting for the neutral hydrogen column density, to answer the question of what is the metallicity in the neutral gas in the universe. And you can see that this metallicity goes down with redshift. So we are witnessing the universe that is evolving in time, and in time building the chemical elements until the point of today where we have what we have today. And this shaded line, the dashed line, sorry, is without taking dust corrections into account. So by taking the dust corrections into account, we could find that there was about 3 times more metals than what was previously known. And if you do this, if you take this dust depletion into account and you consider these abundances, by the way, you can do this with GRBs, but I think I'm running out of time, so let's skip it. Just to say that, so if you take dust corrections into account, you can do a better census of the metals. Where are the metals in the universe? And now the points that I showed you before are these green ones. This is a census of how many, like the metal density. So where are the metals in the universe? Are they in the neutral gas? These are the green points. Then there's contributions for stars. These are the stars. And then more ionized gas. This is the hot gas and ionized gas for the other symbols. And you can see that, and this, like the curve here is what we would expect cosmically. So you can see that if you take dust correction into account, you get this, you get to the notion that neutral gas carries most of the metals in the universe at high redshift. So, at redshift about 2.5. One more thing that we learned was that I mentioned before, dust, the composition of dust is not only made of carbon-rich grains, not only silicates, but also iron-rich. And I will go a bit quickly because I'm running a little bit of time, and I would like to highlight this latest project that I worked on. We answered ourselves, well, what is the metallicity of the neutral gas, the neutral ISM in our galaxy? Until now, the assumption was that the gas is completely mixed, completely uniform, and in the solar neighborhood, it has always the metallicity of the sun, so solar metallicity everywhere. And these assumptions were used for observations, but also in models of chemical evolution of galaxies, where the gas was assumed to be completely mixed. So we ran a HST campaign observing hot stars, like very bright, and using STIS spectrograph with medium-high, well, high resolution. And we observed absorption lines for very different metals: iron, zinc, chromium, nickel, silicon, titanium as well, from very large telescope data, so on the ground with UVAs, and then complemented it with measurements from the literature for H1, molecular hydrogen, and also for titanium. And I'll just show you what we found. Well, just to advertise this, this is coming up, it's forthcoming in Nature in about, well, beginning of September. So keep it for yourself for now, but we're gonna publish this in the first part of September. What you can see here is an artistic impression of our galaxy, and you can see in purple there's the accreting gas that comes in, and it comes in the galaxy, and it does not immediately mix right away, but it has patches. So in this zoom in of this figure, you can see patches which are meant to represent variations in metallicity. So that's what we observe. We observe large metallicity variations in the galactic ISM. And this is one of the figures of our publication, where we looked at the metallicity of our targets. We had 25 targets, and we put them on the galaxy scale. And this is all the way from very low metallicity. So I told you, like -1 is about 1%, sorry, 10% the metallicity of the sun, all the way to slightly supersolar. So in the current paradigm, all the data, all the points should have like about this color, like this dark gray. But instead, we measured that many of these points have low metallicity. The lowest metallicity we measured was 17% of solar. And this was a big surprise. This is a recent image that we made, well, actually galaxy map made, including our measurement on the solar neighborhood. What you see here, it's contour maps of the dust density, medium and high dust density, then hot star density, young stellar object density, cooler star density, and the H2 regions. So you can see this one is the Orion nebula, and the H2 region that was is there. And we plotted our measurements again in this scale of the same scale of metallicity, where you can see that some of them have low metallicities. We didn't see patterns for now, but we hope to make this bigger and map the galaxy with more lines of sight and see if there will be patterns. So what is the basic of my methodology? I think I will go very well. Well, the basics are the fact that we do not assume that the gas has a solar metallicity, but instead we say, okay, the total abundance, gas plus dust, is the observed abundance, which is this one, minus what the dust takes away. So what is eaten away by the dust grains. And then we use, we parameterize the dust depletion in a linear way, where D is it represents the overall strength of the dust depletion. Traditionally, this has been, or in the past, this has been done with a parameter called F star for the strength of the dust depletion from Jenkins 2009. But I told you we could do this with zinc over iron. Recently, we use this zinc over iron fit, which takes all the metals into account. So it's not only a zinc and an iron, it takes all the metals into account. And this is called the relative methods because it's based on the relative abundances. So what we observed, you can see in this plot. These are the dust-corrected metallicities in the different lines of sight that we observe, like this 25. This line here of 0, it's where we expected or where we assume that all measurements are. Then the blue ones are measurements made with the relative methods that I showed you before. The green open circles are the measurements done with the F-star methods. And the yellow triangles are observed zinc abundances, which are virtually a lower limit to the true metallicity. And as you can see, there's clearly large deviation from solar value. This is now like going away from thinking about our galaxy, but this is thinking for different galaxies. Can we use this for different galaxies? Yes. So we expect that the amount of metals in different galaxies is different in different locations. And this is what you can see on the left side for in a simulation, and on the right side in observations. So here they're put on the same scale to compare. So here you can see the stellar disk, so a disk of the galaxy like this, and on the sides you can see like kind of a bluer gas, which is where most of the gas accretes. And this gas is bluer because it has lower metallicity. So lower metallicity gas gets into the galaxy disk, stars are being produced, and then metals are being produced, and then there's outflows that are this time metal rich. So you can see the metal rich outflows and the metal poor accretion. Now this is a simulation, but here Wendt et al. Like found using a composition of for different galaxies and using some of the techniques that I mentioned, they could find the chemical signatures of these baryon cycles. Like they observed the low metallicity accretion disk and the high metallicity outflows. Fantastic. And so this brings me back to my first question, like what is a galaxy? Well, we know now that, and we've been knowing for a long time that gas is really an important measure of, an important component of galaxy for its formation and evolution. Like this baryon cycle of accreting gas and outflowing gas, it's absolutely important for galaxies. And now we are starting to put more and more constraints on the chemical properties of these baryon cycles. And this is very exciting. We are doing this now in Geneva. I wanted to mention my group. Perhaps I will highlight to you Tanita Rambo-III, who is South African. So maybe some of you even know her. And we are focusing on working on interstellar metals and tomography, so how they move around, the inhomogeneities in the gas and the cosmic dust, looking at our Milky Way, but also Magellanic Clouds and distant galaxies. And then I just wanted to finish with a couple of slides about the future, because for these kind of studies, we're very excited about the upcoming new tools that we'll have. In particular, well, there's many telescopes that we will use to tackle the problems of to understand the chemical evolution of galaxies from different observational points of view. One of them is the extremely large telescopes, which is going to be really fantastic to give information really on the chemical properties of the interstellar medium and the circumgalactic medium in galaxies. And of course, the SKA, because the SKA will look at the neutral gas in distant galaxies as well, and it will be extremely complementary to be able to combine the information from the SKA to the information that we get with absorption-line spectroscopy in the rest frame UV, for example. And this will really, I think, be fundamental to study the neutral gas throughout the universe, and also to unveil a whole population of hydrogen-rich galaxies, these ones like the faint ones, small ones, which are normally missed, but we will see them. And yeah, I just wanted to show a number of missions that are coming up. So It's like a bright field, I think. I'm really excited for this one. LUVOIR, that will come in a long, long time, but hopefully sometime this month we will know if it will fly or not, or if it will be on track. And I will just go to my conclusions because now I'm over time a little bit. So first, general conclusions. Gas, metals, and dust are absolutely fundamental for galaxies. And probing the interstellar medium, the metals, at all cosmic times can be done with using stars for the nearby universe, or quasars and GRBs for a distant universe. Then understanding the dust depletion is crucial to study on one hand, the interstellar medium metallicity and its cosmic evolution at high redshift, but also the dust properties, the dust to matter ratio, the composition, the cosmic evolution of dust, and finally also the nucleosynthetic signatures in the interstellar medium out to high Z. And more specific conclusions. So, well, the dust to matter ratio increases with metallicity. DLAs, so distant galaxies, Magellanic Clouds, and the Milky Way, they lie on the same depletion sequences. And these facts, they mean that the DLAs, they behave like the neutral ISM, and it means that the grain growth of the dust grains in the interstellar medium has to be important. And then we found that iron-rich dust is dominant among carbon-rich grains, and that these dust corrections are really important at any redshift. And then the cosmic and chemical evolution, we found more metals out there than what was thought, and this means that the DLAs, the neutral gas bears most of the metals at high redshift. And finally, well, we found large variations in the metallicity of the neutral ISM in the galaxy, down to 17%. Could be lower, in fact, if it is a mix of higher metallicity and even lower metallicity, like the pristine gas. And this means that the infall of pristine gas in the disk can actually cause the existence and the survival of this interstellar medium inhomogeneities. And with this, I thank you very much for your time, and I will be happy to take your questions if you have.
Thank you, Annalisa. Virtual applause from everybody. Yeah, that was a very interesting talk, particularly the exciting new results. If anybody has any questions, please feel free to put them in the chat or raise your hand. I see we already have a question in the chat from Sriram. On slide 16, what is the typical period of variability, and was that plot from a single gamma ray burst event?
So the first question is, what is the typical period for variability, and the second, I forgot.
Were all those plots from a single gamma ray burst event?
Yeah, so the plot was for a single gamma ray burst, and so imagine a gamma ray burst goes off. You see an afterglow first in the X-rays, and then you see it in the optical. You take a spectrum, and then it can vary with very different timescales, but normally it's like within a few hours. So this one was like the first epoch was after half an hour. No, the first epoch was after 8 minutes after the burst. It was like really quick, and this was enabled actually by a mode that is called the rapid response mode, which automatically slews the very large telescope to a gamma ray burst. It's fantastically thought machine. So it could be there, as soon as 8 minutes after the burst. And then after a few hours, normally it's done. This, like the second epoch here was after 1.5 hours or after 1 hour. And there's cases where you can see it's after, 5 hours or something, even the day after, some bright ones, but they are, so hours to a day, that's the typical variability. But yeah, in this picture, you see one single gamma ray burst that changes in time, like it's live, like ongoing change, ongoing ionization and excitation due to the GRB that is happening like now.
Has there been any work with dynamical kinematic modeling to see the expanding shell and how different shells have different ionizations, like the forbidden transitions there?
Yes, there have been some works. So like the modeling that I mentioned here was not so much for the expanding shell. It just took like a radiation and see what happens to the surrounding medium. It was just like a photoionization and photoexcitation modeling of the surrounding ISM. But there has been, of course, like some works, because you expect really that the region that is closer to the GRB to be completely ionized. So it's complex because you don't know what's there, but there has been some modeling indeed. Like, so then there would be like a completely ionized region, and then the blast wave, because the GRB it's not a spherical explosion. You have like the jets. It's a rapid rotating star that collapses, and then there's jets, and the collisions of these jets with the medium then create what is called this afterglow, and that you can see in the X-ray and the optica, and sometimes even in the radio.
Yeah, modeling will be difficult because you have to assume the hardened background and all these things.
But indeed, the radiation is harder than like more at high energy than most sources, because it goes all the way to the X-rays. The afterglow, the prompt can be also in the gamma. The prompt emission of the gamma ray burst itself is in the gamma.
Yeah, thanks.
You're welcome.
I have a question, just on the basic method, or on the a basic question on the method of absorption-line spectroscopy. If you have a very distant gamma ray burst or quasar or whatever, and there are multiple galaxies along the line of sight, then how are you able to differentiate between? Is there such a big difference in frequency and redshift?
Indeed, yes.
Okay.
Yeah. Okay. Indeed, the difference in redshift. So identification of the line system, because it will be specific. There will be specific lines. So identification of this line system is not straightforward, because you have to look at the doublets and what lines from which metals are there. But then a system at different redshift, like if you put another one here at a different redshift, you will have a whole set of lines at a different redshift, so you can disentangle. And sometimes you get systems where you don't know, is it a different galaxy, or are they related and just kind of, you know, in an interactive place, and like an interactive environment where the two galaxies are, you know, in the same, or is it two knots from the same galaxy? Sometimes it happens. It has been observed places where it's not so obvious if it is a different galaxy, completely disconnected, or if it is not. It depends on the velocities of the difference in redshift.
Okay, yeah, okay. And so what kind of redshift resolution do you have then? Because if they are part of like the same group, then I suppose, yeah, it would be, as you said, very difficult to disentangle.
Yeah, normally even with low resolution spectrographs, you can see the difference in redshift between different systems at different from different galaxies. So it's sufficient to have, yeah, normally you can really disentangle the different redshifts. And then with high resolution, when your resolution is really high, then you can go inside the galaxy and see like the tiny movements inside the galaxies. Like, for example, I mean, different galaxies will have velocities that are, you know, different, like the redshift differences in velocity is something like more than tens of thousands for sure. At least, you know, like a quasar outflow will give velocities of that range, but then the difference for different galaxies, like the cosmic difference, is like even like much bigger. But then with a low resolution, with a medium resolution spectrograph, you can get to maybe, I don't know, 30 kilometers per second precision. So it's really like even like already a low resolution is enough to see the different systems, to identify the different systems. With a high resolution spectrographs, you can probe 1 kilometers per second. Well, even lower, like well, there's like the instruments are really pushing the limits, like down to well, much lower, even like a centimeter per second. Well,
thank you. Does anybody else have any more questions? If not, then let's thank Annalisa.
I had a follow-up question.
We have a question. Okay. Go.
So if GRBs are not spherical, then how do we explain the two-component structure that we saw in one of those pictures, like C4 and all those lines had a two-component structure?
I understood your question, but I missed the very first time. If GRB are not, I missed that word.
Spherical, like spherical outflows. That one, that's like
yes.
The two-component structure. Yeah.
So we find more and more that the interstellar medium is not homogeneous, both for our galaxy and also for other galaxies. And what you see here, they are absorption lines due to or produced by gas in a specific position in the galaxy. So it's a cloud, kind of. So you have a cloud here and a cloud there, you can imagine. And the cloud that was here with this velocity was further away than the cloud that was here, the blue complex, let's say, the A and B complex. So this cloud was closer to the GRB. And the GRB itself, like the phenomenon, is not spherical, but then the radiation, when you get the afterglow, it's kind of illuminates. It's conical, and then it opens up even, and then the radiation, you can just imagine we are probing a line of sight. So for us, it's only one line of sight toward the GRB. So we just probe one in the pencil, like one point into this geometry.
Okay.
Did I answer your question, or?
Yeah. I see the zero velocity marking now. I assume it's one side was red shift and one side is blue shift, but yes, I understand now. Thanks.
All right. Okay. It is now past 5 o'clock, so we're not going to take any more questions. Thanks again, Annalisa. That was very, very interesting. And to the rest of you, the link to suggest speakers for future talks is in the chat. So click it now before the Zoom room closes, and we'll see you all at the next talk. Thanks.
Thank you very much. Goodbye.
Bye.